Hello, my name is Giovani Guizzo. I'm a research fellow at University College London, and today I'm going to present to you the paper Sentinel, a multi-objective hyper-heuristic approach for the automatic generation of mutant reduction strategies. So if you're watching this presentation, then you might already know about mutation testing, but I'll start with a quick overview of the topic, just to recap. Basically, you have your original program, you apply mutation operators that synthetically change the code, and then you generate a mutant, which is a buggy version of your software. The objective is to create test suites that can kill those mutants. To kill a mutant, one must execute the test case against the original program and the mutant program, and if the output of both are different, then the mutant is said to be killed. The more mutants you kill, the higher your mutation score. The greater the mutation score, the better your test suite is in revealing the faults represented by those mutants. However, running potentially thousands of mutants against multiple test cases incurs a great cost that still hinders the adoption of mutation testing in practice. There are two main types of cost in mutation analysis: the manual cost of assessing equivalence and the computational cost of generating and executing mutants. In this paper, we focus on the computational cost. In order to reduce the cost of mutation testing, there are several mutation strategies that can be used. Some of them are called do faster strategies, which basically try to execute mutants in a faster way, such as using parallelism, bytecode mutation, and other methods. There are the do smarter strategies that avoid the total execution of a mutant, for instance, weak mutation or checkpoints in the execution of mutants. And then there are the do fewer approaches, which execute fewer mutants, because by executing fewer mutants, the cost of executing them is also reduced. So they do this by selecting mutants or discarding operators. The general idea here is to reduce the cost without affecting the mutation score. However, there are some limitations with conventional strategies. First, there is no strategy that is universally the best in all scenarios. To make things worse, there are so many strategies to choose from and so many configurations that the engineer might get lost. Hence, the engineer must experiment with the possible options to decide which strategy better fits their needs. Another issue is that the strategies are too general. Specialized mutation strategies are necessary to cater for the specific needs of company, project, or the engineer. But the question here is there a way of automating the discovery of such strategies to perform mutation testing in a feasible time without losing effectiveness? This is precisely the objective of our work. For this purpose, we propose Sentinel, a hyperheuristic that generates specialized strategies. But before talking about Sentinel, let me introduce to you hyperheuristics. Hyperheuristics act on heuristic space rather than problem space. In other words, hyperheuristics search for the best heuristic to solve the problem instead of trying to solve the problem directly. So, hyperheuristics, they do not search for a solution. They instead search for the best heuristic that can, in turn, search for the best solution. So, hyperheuristics can select existing strategies or generate new ones from existing components. Also, hyperheuristics can learn online by self-adapting or search for heuristics beforehand for later reuse. With that in mind, instead of using a general heuristic to try and kill mutants, we created an evolutionary hyperheuristic that can create mutation heuristics that in turn can kill the mutants for us. Well, the advantage, the output is a specialized algorithm that's fine-tuned to the program we are testing, considering both cost and quality. How does Sentinel really work then? Well, it first receives as input a grammar with all the rules needed to build the strategy, dictating how the building components can be placed together. Then the solution in a low-level representation goes through a translator to decode it using the grammar into a full working strategy. Then, this strategy is executed to generate and select mutant. Those mutants are in turn executed against the test suite, and we finally obtain the results in matter of cost, in this case execution time, and the mutation score. This result is fed into the training process over multiple iterations, and the hyperheuristic stochastically produces similar strategies to the best one so far, with small deviations. In the end, the best strategy are outputted as possible mutation strategies for the system, and then the engineer can reuse those strategies to test their software. As per usual, we performed a set of experiments to assess the effectiveness of Sentinel. We used 10 real-world systems in the comparison and the pit mutation 2 to create mutants. We have also included 3 traditional mutation strategies: random mutant sampling, which selects mutants at random in a given percentage; selective mutation, that leverages operator information to select only the most relevant mutation operators to perform the mutation analysis; and random operator selection, which selects only a subset of random operators. For the research questions now, we are concerned into answering whether Sentinel is better than a random hyperheuristic in research question number 1. In research question number 2, we compare the traditional strategies to the ones generated by Sentinel. And finally, in research question number 3, we check whether the strategies lose their effectiveness over time, and whether we need to retrain Sentinel in newer versions of the software to generate new strategies. Well, I will not bore you with gigantic tables and a bunch of numbers, so I'll cut to the chase. Sentinel is better than random, as expected, so it passes the sanity check. For research question number 2 and 3, though, we have some interesting results. During the comparison to the other strategies, we found out that Sentinel is able to generate better strategies in 95% of the time with statistical significance. This is an example of the quality of the strategies. The graph here, what you're seeing here, in the y-axis, is the score of the strategies, whereas in the x-axis, you can see the relative cost of the strategy in comparison to the set of all mutants, so the execution time of the strategy. As you can see, the triangles are more scattered in this plot, meaning that Sentinel generates diverse strategies. Also, the strategies show a better trade-off between quality and cost, dominating almost all other traditional strategies. So what you're seeing in this curve here on the left top side is usually the region with the best trade-off between the strategies, and they are almost all from Sentinel. So if the engineer were to pick a strategy here, they would select one that is perhaps in this knee part, obtaining a relative cost of around 15%, while maintaining a score of around 90%. Now answering RQ3, we found out that these results hold for at least 3 newer versions of the software. In 95% of the version updates, the strategies can maintain their results with statistical equivalence. So, after answering the research questions, I'm going to outline here some of the benefits of using Sentinel. The first one is that, well, it performs your experiments for you. It automates the task of finding or creating a new algorithm, and it generates those algorithms with good results. Since the strategies are trained to be as cheap as possible, in the long run, they will save time. They can save as much as 90% of execution cost. Also, training is not necessary every time a new version of the software is released. Thus, the training cost is an acceptable price to pay for such good results. In the long run, this training cost is amortized by the good results. Well, since there is no such thing as free lunch, there are some caveats to this approach. Perhaps these limitations also apply to other AI techniques, so let's discuss them in a specific and then a more broad sense. The first limitation, as some can imagine, is the upfront cost of training, which is non-trivial and is a challenge to overcome. This is true to almost any kind of AI training, be it in optimization or machine learning. However, this cost is usually still lower than manually experimenting with a set of strategies and hand-picking the best one. Sentinel also suffers the drawbacks of the fitness functions that guide it, especially the mutation score. Mutation score is not perfect, it bloats. Multiple papers have shown that a high mutation score of, let's say, 90% is easy to achieve because most mutants are too easy to kill and ultimately irrelevant. That extra 10% is where the gold comes from, but everybody knows that gold is very expensive to extract. Hence, we need better metrics than the current ones to focus our resources on the mutants that really matter. Finally, Sentinel uses a predefined set of components to generate strategies. It does not evolve the set of components, thus there is so much that it can do. One way of improving would be to automatically generate new mutation operators and include them in the loop while generating new strategies. Well, this concludes my talk. Thanks for watching. I'm open for questions.